pumps is to provide flow for the hydraulic system. In this course, you will learn more about the three basic types of hydraulic pumps and understand the differences and similarities between these pumps, their fluid displacement capabilities, and their proper application in a hydraulic system.
Pumps are fluid power components which transform mechanical energy transmitted by a prime mover into fluid power energy. Gear pumps are compact, relatively inexpensive, and have few moving parts. External gear pumps consist of two gears, usually equal in size, that mesh with each other inside a housing. The driving gear is an extension of the drive shaft. As it rotates, it drives the second gear. As both gears rotate, fluid is drawn in through the inlet. This fluid is trapped between the housing and the rotating teeth of the gears, where it travels around the housing and is pushed through the outlet port. The pump creates flow and under pressure transfers energy from our input source, which is mechanical, to a fluid power actuator. The rotating portion of the pump, or rotor, is positioned off-center of the cam ring or housing. The rotor is connected to a prime mover by means of a shaft. As the rotor is turned, the vanes are thrown out by centrifugal force and contact the ring or housing, forming a positive seal. Fluid enters the pump and fills the large volume area formed by the offset rotor. As the vanes push the fluid around the cam, the volume decreases and the fluid is pushed out the outlet port. It is important before viewing this animation to understand the unbalanced vane pump. If you need to review it, go back and click on Unbalanced Vane Pumps. In the unbalanced vane pump, which has been previously illustrated, on half of the pumping mechanism, it is at less than atmospheric pressure. The other half is subjected to full system pressure. This results in side-loading the shaft, while under high-pressure conditions. To compensate for this, the ring in a balanced vane pump is changed from circular to cam-shaped. With this arrangement, the two pressure quadrants oppose each other. Two ports take fluid in and two pump fluid out. The two inlet ports and the two outlet ports are connected inside the housing. Because they are on opposite sides of the housing, excessive force or pressure buildup on one side is canceled out by equal but opposite forces on the other side. With the forces acting on the shaft balanced, the shaft side load is eliminated. Flow is created in the same manner that you have seen illustrated in the unbalanced vane pump, the only difference being the two discharge and two suction cavities rather than one. It is notable that constant volume positive displacement vane pumps used in industrial systems are generally of the balanced design. In this learning lab, axial piston pumps convert rotary motion of an input shaft to an axial reciprocating motion of the pistons. This is accomplished by a swash plate that is either fixed or variable in its degree of angle. With the swash plate vertical, no displacement occurs because there is no reciprocating motion. As the swash plate increases in angle, the piston moves in and out of the barrel as it follows the angle of the swash plate. In actual design, the cylinder barrel is fitted with many pistons. During one half of the circle of rotation, the piston moves out of the cylinder barrel and generates an increasing volume. In the other half of the rotation, the piston moves into the cylinder barrel and generates a decreasing volume. This reciprocating motion draws fluid in and pumps it out.
There are two types of positive displacement hydraulic pumps: a fixed pump, which produces a fixed gallon per minute flow based on the RPM of the prime mover or electric motor, and a variable pump, which can vary its rate of gallons per minute while the input RPMs remain constant. Although displacement is typically measured in volume displaced per revolution, output is measured in gallons per minute or GPM. In this example, a motor turning at 1200 RPM is driving a fixed displacement gear pump, producing 5 gallons per minute flow. The GPM can be changed if the RPM of the motor changes. When a variable displacement pump is used in the system, the GPM can be varied in two ways. As with fixed displacement pumps, the GPM will be changed if the RPM of the motor is changed. The second way is to vary the displacement of the pump. For example, the displacement of an axial piston pump is determined by the distance the pistons are pulled in and pushed out of the cylinder barrel. Since the swash plate angle controls this distance in an axial piston pump, we need only to change the angle of the swash plate to alter the piston stroke and pump volume. Several means of varying the swash plate angle are used. They may include hand levers, mechanical stops, or more sophisticated hydraulically positioned devices. If the pump produces 5 gallons per minute flow with 1200 RPMs at maximum displacement, the GPM can be varied by moving the swash plate into the upright position or de-stroking the pump. This will vary flow from 5 to 0 gallons per minute. Before beginning this section, you should understand the difference between fixed and variable pumps. If you need to review the concept, return to the Pumps menu and click on Fixed versus Variable. Variable volume pumps can also be pressure compensated. A pressure compensated piston pump de-strokes or moves to zero output at a predetermined pressure. This is accomplished by hydraulically positioning the pumping chambers to zero output while maintaining compensator pressure at the outlet of the pump. In this example, we have used a pressure-compensated piston pump. It is helpful to understand the functionality of a piston pump. If you need to review this, return to the Pumps menu and go to the animation for the piston pump. As the pistons rotate around the shaft and follow the angle of the swash plate, they are pumping fluid out the outlet, which provides flow to move a component such as a cylinder. When the cylinder reaches the end of its stroke, pressure rises at the outlet of the pump as the fluid's flow path is blocked. This pressure forces the compensator up, allowing the pressurized fluid to energize the de-stroking piston and push against the swash plate, forcing it to a vertical position. With the swash plate vertical, the pump is now de-stroked and the pressure at the outlet port is maintained at a constant level. A very slight amount of flow is produced to maintain de-stroke pressure. This flow is bypassed into the case and carried back to the reservoir through the pump case drain outlet. Of the three
design, the main components of the crescent pump include the housing with a crescent seal and ports, the end cover, the input shaft, the drive gear, which is an external gear, and the ring gear, which is an internal gear. The drive gear, which has fewer teeth than the ring gear, sits offset in the ring gear. This creates an open cavity between the two gears. The crescent seal, which is machined into the housing, divides this cavity, creating a positive seal between the inlet and the outlet side of the pump. The input shaft turns the drive gear, which drives the ring gear. As the teeth unmesh near the inlet, atmospheric pressure pushes the fluid into the pump inlet. The fluid flows through a kidney-shaped opening in the housing into the cavity between the gears. The two gears move the fluid across the cavity, past the crescent seal, to the high-pressure side. As the gears mesh near the outlet, the fluid is forced out the other kidney-shaped opening to the outlet. A gerotor pump is an internal gear design. The main components of the gerotor pump include the outer gerotor element, which is an internal gear, the rotor or internal gerotor element, which is an external gear, the input shaft, and the housing with the ports. The rotor, which has one less tooth than the outer gerotor element, sits offset in the outer element. This creates an opening cavity between the two gears. The two opposing teeth divide this cavity, creating a positive seal between the inlet and the outlet. The input shaft turns the rotor, which drives the outer gerotor element. As the teeth unmesh near the inlet, atmospheric pressure pushes the fluid into the pump inlet. The fluid flows through a kidney-shaped opening in the end cover to the cavity between the gears. The two gears move the fluid across the cavity, past the opposing teeth, to the high-pressure side. As the gears mesh near the outlet, the fluid is forced out the other kidney-shaped opening to the outlet. A variable displacement pressure-compensated pump is designed to respond to pressure changes that occur in a hydraulic system. There are several advantages of a pressure-compensated circuit: energy conservation, better controllability, and concurrent actuation of several circuit functions. Some of these advantages may be offset as a result of higher component costs. A variable displacement pressure-compensated pump is most often used in a closed-centered system. In this example, we've used a pressure-compensated pump. It is helpful to understand the functionality of a piston pump. If you need to review this, return to the Pumps menu and go to the animation for piston pump. In this example, when the control valve is in the center or closed position, the pressure forces the compensator spool to shift up against the spring setting, allowing the pressurized fluid to shift the control piston and the swash plate to a vertical position. When the swash plate is vertical, the pump is now at zero stroke or no flow, and the pressure at the outlet port is maintained at the set pressure. A very slight amount of flow is produced to lubricate the pump and maintain compensated pressure. This flow is vented through the pump case drain port. When a circuit is actuated and the pump control senses a pressure drop, the spool shifts away from the spring and fluid is vented from the control chamber into the case of the pump, and the swash plate rotates on stroke to produce the pressure and flow required by the actuator. Of the three types of hydraulic pumps discussed, gear, vane, and axial piston, only the vane and piston may be pressure compensated.